Hi, everybody. So we have 1 o'clock now. I think we'll work on slowly getting started here. Rian, so my name is Eric Putnam. I'm head of department here at Force Technology within the area of materials testing. I'm joined by my colleague today, Rian Holdstock. Rian is a project manager in our unit for materials testing, and Rian and I are going to give you a presentation today, a webinar on what we've entitled Introduction to Fatigue Testing. So we're starting quite broad and on an introduction level to just kind of, it's of course hard for a webinar to know exactly who's going to be taking part. So our goal is here to give some general background information, but really then throughout the presentation, get a little bit deeper and talk about a couple of case examples to provide some interesting discussion points as we go throughout the webinar. Rian, can we take it from the top?
Sure.
So, as I said today, general introductions. I'm going to do just a little bit of background on Force Technology so you know who you're meeting today. We're going to, as I said, walk through the background of fatigue. What is fatigue? How do we look at it from a testing perspective, both in a small-scale laboratory but also full-scale testing facilities? How do we do measurements in fatigue testing programs? And then all these measurements that we've done, talk about the analysis of results. How are we using the results, the data from the tests we've used? And finally, round out with 2 examples, some real cases we've been looking at here at Force. So now I will just go into a little bit on Force Technology and who we are and what we are as an organization. Keep going, Rian. You can just, there we go. So Force is a technology service provider. We are headquartered in Denmark with about 30 sites in Denmark, Scandinavia, and smaller locations throughout the world. We are a testing, inspection, and certification company. Now, we have basically 4 service models that we're working with our customers. Number 1, inspection, measuring, data acquisition. This is really where we're going out to our customers and doing service at their facilities or in the field. Testing, calibration, and analysis. That's where Rian and I are coming from. That is usually where the customers are sending their products, their materials, their items to us, and we're doing testing on them in our facilities. Now, we do as well then products, components, and sensor systems. Have some products that we make, for example, ultrasound scanning solutions for non-destructive testing. So we provide some specialty products and services to the industry. And finally, training and consultancy, you can see as kind of an umbrella around these services. We have some specialized training programs, but also do some other more custom courses. We're about 1,100 employees, again, heavily headquartered in Denmark, but in Scandinavia, but some smaller sites throughout the rest of the world. If we keep going, Rian, one of the unique pieces about Force is our number of facilities. We have a lot of test and demonstration facilities, calibration, and you're going to see some of those facilities as we're running through the presentation today. Our purpose here is not to talk about the facilities in themselves, but it's just about how we're using these facilities to provide the services that we do to the industry, our partners, and our customers. And on the perspective of partners, we work on quite a significant number of collaboration projects and also research and development projects yearly and on a continual basis. So, Rian, could you go to the next slide? And those research and development projects are really stemming from the fact that Force Technology is a research and technology organization. We are in Denmark recognized as one of the 7 GTS institutes, or these research and technology organizations, that were established by the state of Denmark to make sure that the Danish industry has a strong foothold in what are the emerging and developing technologies to ensure access for the industry to these areas. And Force is the largest of the GTS institutes in Denmark. But as you could see on the earlier slides, we are actually still quite a international organization. So while we have this status in Denmark and it enables us to work on research and development projects, some of which you will see in the presentation today, we are working globally and internationally with many different customers from many different segments. So Rian, I'll pass it to you to get now into fatigue testing.
Thanks, Eric, and welcome everyone. In case you forgot, my name is Rian Holdstock, and I'll be sharing the presentation today with Eric, and we'll talk you through an introduction to the testing. This is a pretty big area and it covers a lot of things. We won't be able to go through everything. Our aim today is just an introduction and show you a few things that perhaps you haven't known, or maybe you need to consider in a different light. If we look at mechanical fatigue, what my plan is to go through a few key phrases with you. And what those phrases will do is it'll hopefully get all of us onto the same baseline, so that when something is mentioned later on, then it could be understood where it came from. And here we can see some examples. Now, the basic description of fatigue is that it's the weakening of the material due to loading and unloading. And what we know now is that it's the growing of cracks through the material that then creates the fatigue damage. We've got two types of fatigue. We've got low cycle fatigue and high cycle fatigue. And the low cycle fatigue, it explains the few cycles that occur above yield, whereas high cycle fatigue describes many cycles that occur below yield. Very specifically, I'd like to introduce these four specific variables or phrases with you: stress range, the R ratio, the stress amplitude, and also the loading condition. As we'll see a bit more of this later on. So if we first look at the stress range, the stress range is your maximum stress minus your minimum stress. And the stress range could shift. So these are not fixed values. And that's a key point, because when we devise our tests, or when we do investigations, we can shift this stress range, and that can help us target specific areas, specific focus points. Then the next thing that's important is something called an R ratio, and the R ratio is your minimum stress divided by your maximum stress. And I'm assuming everyone knows the terminology tension compression. So if your minimum stress divided by your maximum stress, if the answer is positive, then you have a tension test. If it is negative, then you have a tension compression test, and if the R ratio is 0, then you got a pulsating tension load condition. And we'll see now what that means. The other thing that's important is this amplitude, the stress amplitude. It could be a constant amplitude, as what we see on our left, or it could be a variable amplitude, what we see on our right. So let's look at that tension compression loading conditions again. If we look at the graph on the left-hand side, you can see it's above that black line, that dark line. Now, what that dark line means is that the stresses are positive. They're in tension. So the The fatigue loading condition there is tension, tension, because we have everything happening in positive stresses. If we look on the right-hand side, we have a tension compression loading condition. And what that means is that some of our stresses are positive and some of our stresses are negative. And I think it should hopefully be relatively obvious to join the negative with the compression and the positive with the tension to make this understandable. Okay, so we looked at very quickly at mechanical fatigue. As I said, it's a pretty big area. We looked at the loading conditions. I think the key thing there really is that it's not fixed. We can adjust things, and that's one of the key things that help us to target specific conditions, and that then allows us to get better results during the fatigue testing. So now we'll look a little bit deeper, and we'll pull the microscope closer, and we'll have a look at what's actually happening inside the material. So what we can see here is we see a typical fatigue crack in a weld. And during fatigue damage, let's call it that, there are two things that are happening. One is crack initiation, and the other one is crack growth. Now, it is different depending, in this case, whether it's a weld or whether you're just looking at a machine part. That the experts tell us that for welds, the crack initiation uses around 10% of your fatigue life, and while crack growth is around 90%. So let me explain it differently. It means that to originate, to create the crack, it's pretty quick and not a lot of energy goes in there. Where all the energy is consumed is during this crack growth, because in a weld we have a lot of small defects, and these defects then have to link up, and the crack has to grow through that. These values are approximate, so they're not. They will be different from case to case, but they're general values. And here are a few more. And what we can see is that a fatigue crack it's almost a straight line. It looks like someone has taken a sharp object and put a mark on this steel. That is first indication that, all right, this is probably a fatigue crack that we're looking at. And if you do see, if you've seen a few of these type of metallurgical features before, you'll realize that we can tell a lot by how the crack propagates through the material. So yeah, notice the straight lines here. And when I said how the crack propagates through the material, typically in fatigue, we've got something called beach marks, and they are created by this repetitive loading and unloading. And it's called beach marks because it's very similar to the sea, to the waves. If you've sat on the beach or even in a lake, you will see around the lake edges or on the beach where the water washes over the sand, and it leaves and it comes back and it washes over the sand again. It leaves these marks, these lines, and that's what we see in a lot of fatigue cases. So that's when we look inside beach marks. We see these beach marks. So that is a quick introduction to mechanical fatigue and to the microstructure. We're building up the presentation. We'll see a bit more. Now we have a 2-minute break maybe that we can stop and we can see if anyone has questions related to what we've just discussed. If you have, please put them in the write a message to us, and one of my colleagues will collect the questions and then ask us. So let's see if there are some questions now. Ahmed, do you have any questions? Any of my other colleagues there have?
Well, yeah, we have a question here. How do you tell the difference between crack initiation and crack propagation?
Okay. So how do we know which is which? Let me just go back a bit. How do I know whether it's a crack initiation or crack propagation? It's pretty difficult. And the reason why it's difficult because there's so many things happening there. The normal method that we use is we look at the size of the feature. If it's around 1 millimeter, then we make a strong assumption that that is crack initiation. If it's less than 0.5 millimeter, then it's crack propagation. So that's how we tell the difference. The other thing you can also try is use acoustic emissions to try and hear, because when the crack starts, it releases energy, it makes some noise. Or you could try running a voltage through it, and when the crack starts, there'll be a voltage drop. But these things are a little bit difficult to do. Okay, so what I think we'll do is, thanks for that question, and please send your questions in. If we can't answer them during the presentation, we'll try and respond in the next few days and get an answer for you.
We have another question, Rian.
Yes?
Isn't the fatigue life of a structure defined until crack initiation?
Yeah, another good question. No, because it's one of the things that needs to be discussed, but normally during testing, we will look at it from the other way. So we will either wait for a certain amount of cycles to occur and then stop the test, or we'll wait for a through crack to occur. Now, what we also need to say is that there are a lot of structures out there that have cracks in there, and they still have fatigue life. So a crack doesn't necessarily mean that it's the end of the world. It just means we have a flaw now that is noticeable, and we need to find out how to deal with it. And as you'll see later on, there's also certain values where the theory tells us if we keep the stress below a certain value, then we shouldn't have fatigue damage. But thanks for that question. What I'd like to do is just move on and talk about laboratory testing. These are relatively straightforward. It's small scale, and the sample, as long as the sample or the product can fit in the machine, we can do the fatigue test. The benefit with modern technology is we can do these tests very fast, and you know, we can do a million cycles a day. It's pretty common. So the duration can be pretty quick of these tests. In the old days, when especially for larger samples, it took many days, weeks to reach millions of cycles. But we've now got the electronics and the hydraulics and the computer software, so that they can generate a lot of cycles. And what we see here is a typical test setup, where in the middle you've got the specimen, and on the top of the bottom you've got the actuators. Now the fatigue loads, they are determined. So the settings, how do we know what variables to use? This is a specific agreement between the client and ourselves, or we can reference a code or a standard that can tell us what to do. We can also look at experimental data, and that can tell us how to do it. So there's several ways. I would say a lot of the work that we do, it's prescribed. You just open up the specification, you follow the specification, and that gives you the results. Okay, so break from me now, and I'm going to hand the microphone over to Eric.
Yes, thank you, Rian. So we're going to look at a little bit now the other end of the spectrum, full scale. As Rian said, so we're going to go from what is, in some regards, prescribed methods that, in the laboratory where we're very often looking to generate data, we're very often looking to generate characteristics that might be made to use for actually using the design process. And we're going to go to a little bit larger size scale, full scale, where often, or you could say component and up to full scale, where often we're doing testing more for a verification case. We're looking to try and see that the design and manufacturing process is working, and that the fatigue can still that the fatigue life is still there as required for the use of the structure. And here I just took a wind turbine as an example. Over on the left-hand side of the slides, we actually see a turbine sitting. We see a full turbine sitting in an offshore installation. And that would obviously be our ideal testing environment, because we have the real product there, we have all the components have their real boundary conditions, they have their real loads, but yet these installations will have design lives of around 25 years. And so if we want to test it, we actually have to build the product, we have to install the product, and we have to test it in the field. It's the ideal environment, it's going to tell us what's happening, but we are not going to learn about something until it's too late. So that's where we actually use testing facilities. We use test setups in component structure test benches, such as the one pictured on the right, which is actually these are 3D generations of facilities that we are doing testing work in. And here I've just grabbed a set of illustrations that basically move from a base case, an empty testing facility in the upper left, showing some adapters, some hydraulic cylinders on the floor, to give the impression that really the facility is kind of a blank canvas. It's about building up the test program that's required. And the other test options here, the other test possibilities are, in this case, also trying to show components from wind turbine that can use this endurance testing, lifetime testing, where we're looking at possible fatigue aspects happening. Upper right would be a back-to-back gearbox test. Bottom left, looking at the testing of a main bearing from a turbine, and bottom right, actually the testing of a pitch bearing from a turbine. So you see, wind turbines are good examples of working in the case of fatigue testing, because they are high demand components that have these variable amplitude loads that are applied over the 25-year lifetime of a turbine installation. So what we're trying to do in the test bench then is actually create a representative setup, a testing case for how we can implement that, and shorten that 25-year lifetime into a much shorter testing time, usually something around a few months of time. And we do that by actually scaling the loads, taking those very small variable amplitude loads over 25 years, shortening them and making the loads bigger to be able to accumulate the same kind of fatigue damage. Can we keep going, Rian? So here, I actually just then, kind of wanted to do a little bit of comparison between small scale and full scale to give an idea of, kind of in which cases we might be looking at using small scale testing, and in which cases we might be looking at full scale testing, because there are always trade-offs in going one route versus the other. For example, small scale tests, they are in the name we're using, they're much smaller, they're much less resource intensive. So we can do a lot more small scale testing for the same budget that we can do in full scale testing. But we are going to be looking at different things. Small scale tests are very good for generating material data, for generating data that actually needs to be used in the design process of a product. But it's less applicable when you're actually looking at your real product, your real configuration, and you want to see how some of those design or manufacturing elements get represented, which you can actually bring into a full scale or a component test. We'll hear a little bit more about component testing later in the testing examples. So part of this slide here is just to think about making sure when we're looking at a fatigue testing program, when we're trying to identify what is the right route for doing testing, that we take the trade-offs into the different tools we have. We take the trade-offs into account from the different tools that we have available. And so one point that Rian discussed earlier when he was discussing mechanical fatigue was he was talking about the stress ranges. He was talking about the loading conditions, and we've heard elements of the constant amplitude and variable amplitude. And now one of the things that we need that's very important then to be able to assess these conditions and understand what we're getting in a testing program from small scale to full scale to even if you were doing testing in the field is actually instrumentation. Instrumentation or measurements are what give us that data that we're able to learn from our test programs and then actually do computations with. I've here broken really down the data that we're receiving from a test program into 3 levels, where really kind of global. How is that overall test specimen behaving? Nominal. What would be our average stress response? The stress response that's occurring away from any stress concentrators. And then a local detailed level, a hotspot stress response, a stress response that if we go back to that microstructural example that Rian showed earlier, what is that stress right at the weld toe where that crack first started? Because all of these pieces, all of this kind of data builds to give us our picture of the mechanical loading and also the fatigue response that we have. Rian, can you go to the next slide? So here we actually just pull a couple of examples. The picture on the left is very much the picture we saw before, but just this time zoomed in a little bit to where we can talk a little bit more about a couple elements of the system and also some gauges that are mounted on the specimen. So within a test frame, you actually have measurement sensors that are integrated. In that test frame, you have load cells that are able to give us the load input that we are putting into this test specimen. We also have displacement sensors built into the test frame. Or if the displacements within the actuators within the test frame aren't accurate enough, we can actually put displacement sensors right onto the test specimen and measure local displacements, or still these nominal displacement levels, the average responses. If we go from the frame, the overall specimen dimensions down to the smaller dimensions, getting closer to any hotspots, we actually see a number of we see wires coming off of this specimen. That's because we've mounted strain gauges here. And by the use of strain gauges, you can see some individual strain gauges in the picture on the right. They're the small patches that are glued on the specimen. By using strain gauges, we can actually determine the stress that we have on any given test specimen. On the right-hand side, you can see that we have a very kind of detailed, fine picture of all these strain gauges that are put in place. And that's because in this case, we were really trying to assess what was the hotspot stress that was at these weld toes on these different pipe sections that are represented here. And that's where we're going from the left-hand side. The strains were mounted further away from any kind of disturbing points, whether it be a hole in the specimen, whether it be a weld, whether it's something glued or bolted on. all of those would be causing stress concentrators. And if we're measuring close to them, we're measuring that local response. If we're measuring further away, we're getting this bit more global response. Or no, yes. So that's the piece here on instrumentation.
Thanks, Eric. Okay, so what we've seen is we can go small scale, we can go large scale, and then we do the tests, and there's a lot of data that's generated by these tests. And hopefully some of you out there are thinking, okay, what do we do with this data? Help me understand it a little bit. And the next few slides will hopefully do that. It won't explain everything, but it'll tell us a little bit more. Now, the fatigue strength or the fatigue resistance can be shown by what's called a SN curve, and that's a stress number of cycles curve. And it's a plot, and on this plot for the theoretical curve, there is something called a knee. And if we plot the data points, what that knee tells us, it tells us that data points below the knee, we're not expecting fatigue. Fatigue hasn't started, and it's going to be okay for another 10 million cycles. This is also known as the endurance limit or the fatigue limit. Now, not all materials have that. This is just a theoretical case, and it's simplified to show that the fatigue behavior is not linear. It does change. And that for some material, for some stresses, for some loads, we're going to get less damage compared to others. And also quite generally, we see that our fatigue strength can be derived by after we've done the test and we've got all the data points on the plot. And the plot will look similar to this. We will then, we can then approximate what the fatigue strength will be at a specific number of cycles. And we can also see whether any fatigue damage is likely to occur. Now, if we look at something more realistic, what we see here is something that was developed for wells. And on the right-hand side, you see all these test samples. So they did many tests using standardized geometry, samples like this. There's a whole book full of these samples, and they plotted the results, and they said, okay, we can now standardize it, and we can create these specific fatigue curves or these standardized fatigue curves. And what we see here is we've got 100 and we've got an 80. That's sort of, if you look at the plot, you'll see there's a square with 100 and a circle with 80. What that tells us, it tells us, if you say that this is your guide. So one way of doing testing is we follow the book. We use a standard specification. So, and the standard or the specification or the code will say you have to achieve this. So we then do the test and we plot it on there, and it will look something like this. Now, what those numbers mean, if we look here, we see 40 to 160. So the higher you go, the top curves have a better fatigue life. And if the requirements are a lot more stringent, then you want a better fatigue life. So you'll be asked to produce something that is towards the top. And of course, it's the other way around. If it's not so critical, then the fatigue life can be less. And here they refer to as a fat class. So let's look at 100, what that means at 100 megapascals, it must give a fatigue life of 2 times 10 to the power 6 cycles, or number of cycles. We must reach that. If we don't reach it, then we haven't fulfilled the design criteria. So the example I'm showing you here is from a standardized method, and it's a prescribed method. It's just follow the rules, and we have to meet a very specific criteria. What we can also see is that they also show the effects that constant amplitude and variable amplitude will have. We can see that variable amplitude will have create more damage at lower stresses. Okay, I know we're going quick, and it's a big subject. So let's see if there are any questions out there.
Yeah, Ryan.
Yes.
First off, we have a question for the last slides. I don't know if you want to take that now or last.
Let's go for it. Let's see if
Okay.
we can answer.
So the question is, can you model fatigue and the cracking by, in example, FEM methods? Can you predict it by material parameters?
Yes, you can. If you just use your, you can predict it, and then you don't have to do the these curves. And I think maybe that's, if I'm turning the question around. Yes, you can do numeric methods. You can use finite element analysis, and you can guesstimate the fatigue life from there, and it can also be accepted. It all depends what the needs are and whether you want to accept the conservative results, but definitely. And it's something that we touch on later as well, that you can also go the numeric way. So yeah, the answer is yes. Yes, you can do that.
Okay, now we have a question for this break, and the question is, well, these fatigue lines will be hard to define for turbines when operating with dynamic loads. How do you then calculate?
Eric? So how do we calculate the fatigue life?
So if on these turbines where we have the high dynamic loads, we have the high variable loads that are happening out in the field, there are analytical analysis methods that can be used to reduce these loads into basically an accumulated damage quotient. And one of those methods is called range flow counting. It basically looks at the summation of the amount of full stress reversals that you've had on that component. And it makes it so you can relate the accumulated damage in that case to what the accumulated damage is in a simplified case in the testing laboratory, where we would do constant amplitude, and the cycles in that regards then are very easy to count, like those cycles we saw earlier. And of course, there are certain simplifications that you're taking there. Those simplifications are also simplifications that are accepted by some of the standards that Rian was mentioning earlier, that can give you some guidelines in how to set up fatigue testing programs.
Thanks, Eric.
Yeah. Okay, we have one more question. Have you conducted very high cycle fatigue tests, sub 200 million to 25 years, that prove the existence of an endurance limit in this cycle range?
I'm gonna start answering it and then give it over to Eric. It's a very interesting question, because of course we know that there's a theoretical discussion that there is no such thing as endurance limit. If you do enough cycles, it's going to fail. So the question then is, if I understand it right, is saying, okay, have we done any tests to prove that? And Eric, what's your take on this?
We have been working on some test programs where we're doing plus 100 million cycles. This greater than 200 million, and that would be at the small scale level. That's in our machines where we can run fastest, plus 100 hertz, up near 150 hertz in some cases. But really significantly greater than 100 million cycles, we have not had experience with testing programs on yet. So but I am with Rian that there are discussions. We are aware of discussions whether an endurance limit truly exists or not. And I think in some regards, the point of introducing it here was also just to give the indication, not necessarily if you're under the endurance limit, can you say check mark your fatigue life is okay, but minimum to introduce this point that there is a change in slope of the fatigue curve, that after you've passed that knee, you have a much shallower slope and a much longer potential fatigue life.
Great, thanks, Eric. Okay, we've got about 20 minutes of your time left, so I'll crack on and start introducing an example here. What we can see here are high-strength steel bolts, and they're situated in a moist and salty environment. And these things do undergo fatigue damage or fatigue loads. They do see fatigue loads, whether fatigue life, everything has a fatigue life, and everything you do to that, you consume that fatigue life, you reduce it. So bolts have to be installed, they have to be tensioned and torqued, and then not all of them are going to be exactly the same. And then if there's movement, if the structure breathes, if you have a large structure and you put it out in the sun, it's going to grow. If you put it out in a cold wind, it's going to shrink. So these things do see fatigue lives. So we've got these high-strength steel bolts situated in a moist and salty environment. And then we also have small defects on the surface. As with most steel structures, there's a defect somewhere just waiting to emerge. And then the questions we were asked is, well, we've got these defects, we've got these loading conditions, we've got these stresses. What is the remaining fatigue life? How many of our bolts will fail? If these bolts fail, what does it do to the other bolts? How does it change their fatigue life? And do we need to replace all of the bolts, or could we only replace some of the bolts? And then how frequently do we need to inspect this? So what you can see there is from fatigue testing, we can answer, or fatigue testing program, we can answer a lot of questions. That's not just about the material itself, but it also helps to make decisions about when do we need to do the testing? Do we need to have repair campaigns? What do we need to order? What sort of risk is involved? Now, I've mentioned bolts here, but we can replace the word bolt and we could put, I'm going to say anything, but within quotes, we could put anything in there. The general formula is going to be the same. There's a lot of harsh environments out there, and there are a lot of strains, a lot of stresses, a lot of loads that these structures have to deal with. So what's the solution? Unless you really just want to pass a test, get a tick in the box, go through the steps, you're normally looking at a bigger scope where you have to combine other things. The fatigue life does depend on how well the material can resist crack growth. And it's normal that a hybrid approach is then used, where you need to, like in the case that we just showed, we need to use fracture mechanics. We need to do some additional physical fatigue testing. We need to do metallurgical analysis. And as Eric showed earlier, we need to instrument it. We need to understand what is happening to those strains, what is happening to those stresses. So the message here then is that fatigue testing is if you do it if you want to get a tick in the box because it's a requirement from then it's an easy approach. But if you have an issue and you want to find out what's happened and what your options are, what the risks are, you need to go for this hybrid approach and bring in some of the other specialisms. Okay, I'll pass back to Eric to talk about a second example.
Yeah, so this is our last example, and it will also bring us towards the end of the webinar. So here you're actually seeing some test campaigns that we have done and are still actively doing as part of some industrial but also development projects. We've had a number of development projects related to offshore wind foundations, particularly jacket foundations. And in those programs, we've done testing campaigns from what you see on the bottom, small scale specimens that we were able to do in those test machines we were talking about earlier, up to full scale specimens that need to be put on a component and structure test bench, a mechanical test bench that can react to those heavy loads that we're seeing when testing these full scale structures. And then in the middle, you can actually see a specimen that still is looking representative of a jacket node, but this specimen actually is about half size in comparison to the one on top. To just give relation to the one on top, that yellow node, the piece in the center that looks like a K, that's actually about a 15-ton specimen. The main pipe, the big horizontal one, has a wall thickness of 60 millimeters. And in this test program, where we were actually testing the welds between the brace, the small pipes, and the big pipe, we actually were going to fatigue failure, full through thickness crack is what we defined as failure. So we had to grow that crack. Actually, it ended up initiating in the big pipe, in the cord. So we had to grow it full through thickness of the 60 millimeter material. Those was one of the crack cross sections that you saw from Rian earlier in the presentation. So on the small level, we were actually looking at more just kind of how do welds perform under fatigue in these dog bone specimens, but more of a generalized specimen. Up top, we took an actual joint out of a real design, a real jacket solution. And then now in the middle, where we're looking at these components and elements, we're trying to look at a specimen that's more realistic, more representative of the real geometry, have thicknesses that are closer to the real size, have better control of the boundary conditions that weld is susceptible to, but still be able to design a specimen that creates less resource intensity in terms of materials, number of man hours to weld it, and then also one where we can use smaller loads to get to higher stresses and run faster, get more specimens run through a testing program. Rian, can we take the next slide? So here you can actually, you saw the picture on the right already, but just to give a little bit more about the testing examples here that we actually did on the full scale jacket nodes, we did two different loading cases. The one on the left, we were actually testing an out of plane bending. So we were trying to get fatigue failure on the bottom of the weld because we ran a load program where we did the braces in tension. So when we pushed up on the hydraulic cylinders that are located on the bottom of the brace closest to us, we pushed up and then went back close to zero. We ran within our ratio of 0.1. So we always had a tension load case. That was really to force crack opening. If we're going into compression, you can think about we're actually, for part of the stress cycle, closing the crack. That fatigue damage would still be counted, but it's more conservative to always do a tension load case. So that's what we actually did in both of these programs, was tension load cases to really try and force that crack opening and force failure, because it does take time to get that failure in these specimens. In these programs, we were actually able to run 1 Hertz, and we were getting, we had fatigue lives between with fatigue lives over a few million cycles in some of these specimens. So we were running for many months, which is, in some regards, quite a contrast to the fatigue programs we saw on the test machines, where we can, on some of those machines, I said we can run around 100 hertz. That's actually getting us 10 million cycles in roughly between 24 and 30 hours if we're running those high cycle test machines. So just to give a quick picture of some fatigue testing in real life.
Thanks, Eric. And this is probably the second last slide we have. So you've got time now to ask some questions, and let's see. Ahmed, do we have some? Okay. Well,
yeah, we just got a question.
Okay.
How do constantly changing environmental influences, example given temperature, during outdoor testing affect the target loads? If yes, how do you react to these changing conditions?
Eric, is it?
Yeah, I can take a stab at that one. There are, of course, certain concerns for the environment that do have to be taken into effect. And you will also see that in the fatigue curves within different standards. For example, in air fatigue tests versus fatigue underwater or saltwater conditions, because saltwater can be particularly aggressive towards fatigue life. We in our testing programs have there's the laboratory testing programs, and then there's also the in field testing programs. These more full scale tests we've done. We actually have in all of our testing programs, we have a measurement of temperature. We keep a log of the environmental conditions. I cannot say that we've done a particular mapping we have not done a particular mapping of whether the environmental influences affect the fatigue life, for example, in the open air test bench. But it is a very good point to take under consideration.
And I think also some of the specifications they have I don't know what it's called, but there are additional calculations that you can do if you experience certain conditions, like excessive cold or excessive heat. If there is going to be a change in geometry, that'll either like knock down factors or knock up factors, which can adjust it. I've seen it. I haven't used it, but I have seen them being used. And also, it's as an example, if you have your fat class, if you have thicker samples, the fat class can change. So there will also be conditions where the work that we do analytically, it has to be a little bit different, and then there's some things that can be added. But I've only seen this. I have no experience with it. Okay. Ahmed,
one more question. Actually, two more. Do you also have the possibility of adding seawater and cathartic protection? I ask because cathartic protection or free corrosion will have an influence on fatigue life.
Yes, to everything. It definitely is possible to do that, and also corrosion fatigue is difficult. This is what I mean by difficult. Is there's a lot in it, and there are a lot of discussions. There are a lot of things that need to be done, and if we throw corrosion into it, it makes it even more difficult. But yes, it can be done. we can do it in seawater. We can do add cathodic protection or cathodic charging to see what effect that has. The test setup has to change, and also many times the duration has to change, and for some things they need to be pre-trials. So what I'm trying to say there is that if a standard fatigue test takes so long, if we do some of these specialized tests, we normally have to do something in a reference environment, which is a neutral environment, and then do something in the aggressive environment. So in effect, you're doubling the test duration of the test. And for those with money, you also for the cost of the test. Eric, anything you want to add to that?
No, I think that's a good that you had a good point, Rian, and that yes, it is all possible, and we actually do have examples of having done fatigue testing or actually even fracture mechanics testing in simulated seawater. More so at the small scale laboratory size. We have not done it full scale, but it's all, let's say, within the realm of possibilities. Just, it's about what are the specific investigations, the specific results that we're looking to try and characterize.
Okay, guys, we have one last question. Would FORCE be able to determine causes for a fracture in a specimen that has already failed? Can anything be said about causes being material fault, weakness, or excessive forces?
Yes, we can. We can. Now, what if you read reports? You'll typically see that what the intelligence likes to do, or the investigation, they tell you everything. This is what we see. What you're normally going to end up with is it's probably going to be, unless it's very clear, it's going to end up being, all right, it's either this or it's or that. That's my experience. So you'll be sitting with a choice of which one to use, and of course more work can be done, and then we can get closer to saying this is exactly, it's this one. But prepare yourself that you could end up with having two answers. But to answer the question is yes. It's one of the things that FORCE does a lot. We investigate a lot of fracture surfaces, and we predict what's going to happen if the thing is still in service, and we could also say this is what has happened. And there's also a whole lot of other packages that can be added. So a fitness for service, a type investigation, or engineering critical analysis. So not only can they then say, this is what happened, but this is the risk, or this is potentially what can happen if the structure isn't still in service, or if there are other structures, like those bolts that we saw earlier. So there were a few failures, but it wasn't the end of the world. We could show that the structure will still be okay, and that quite a few of the bolts could break. When they designed it, they designed it quite conservatively.
So Rian, I think it's time to head to the last slide.
We have one last question.
Ahmad, I think maybe we'll collect the questions that we have remaining, and then we'll be able to follow up with those that sent any additional questions we couldn't get to individually. We just have 1 minute left here, and we promised everyone to only take their time up to 2 o'clock. So I want to make sure we send everyone off in time. So I would very much like to wholeheartedly say thank you to everyone that joined us. I hope it was interesting. It was great to have you. Thank you very much for the questions, and even if the dialogue was a little bit one-sided, it was great. And I would actually like to give a preview that we would like to follow up with an additional webinar in a couple months. So look out for the materials testing newsletter we're actually planning to organize somewhat of a small online seminar and not just have FORST represented, but invite a few of our project partners and some institutes that we collaborate with to give some interesting testing examples and interesting cases that they're working on as well. So keep an eye out and we will be in touch. Have a great day, everyone. Thank you. Bye.
Thanks, everyone. Thanks for your questions, and have a great day wherever you are. Ciao.